Yeah, we see your screen.
Okay, great. Shall I start?
Just a small introduction on you.
Oh, go ahead. Yeah.
Mine. So we have the pleasure today to have Mehrdad with us. Mehrdad is a postdoctoral associate at MIT, and he received his PhD at Georgia Tech, and previously attended University of British Columbia and Sharif University. And his interest broadly lies in optimization, algorithms, numerical linear algebra, and applications of this in machine learning and data mining. Also, he has worked on theoretical problems, and he's passionate about designing practical algorithms that incorporate societal considerations such as fairness and privacy. We are happy to have you here, Mehrdad, and the floor is yours.
Yeah, thank you, Farzan, for the nice intro. So yeah, this I kind of like combined like two different papers for this talk because they're like both about like Tucker decomposition, so I thought it would be good to talk about both. I did these with a group at Google when I was doing an internship there. I think 2 summers ago, maybe 3 summers ago. And yeah, let's get into it. These are the papers that I'm going to talk about. One is published at NeurIPS, and it is about like a faster algorithm for like Kronecker regression and how it can be used to speed up like the alternating least square for Tucker decomposition. And the second one is about like finding the best shape for our tensor when we are trying to pick like what should be like the dimensions of our core tensor. With that, probably like this group doesn't need like motivating tensors, but I have a slide for that. So let me just briefly mention that like the way I think about like tensors, at least in these two papers, is like as like multidimensional arrays of numbers. So these are just like some array of numbers. Like other people, like a lot of mathematicians, physicists think about this as like multilinear operators or something like that. This is not like what I'm considering here. It's just a bunch of numbers. And then they have like a lot of applications across like sciences, engineering, machine learning. Like fMRI is essentially just like a 4-dimensional tensor. 1 dimension is time, 3 dimensions are location. Like you can model like a regular hypergraph as a tensor. Like if it is like a 3 regular hypergraph, each vertex in an edge is like you have like 3 dimensions if it is like a 3 regular hypergraph, and each dimension corresponds to like one of the vertices in that hyperedge. Knowledge bases, like, you want to model like a sentence, like he ate an apple. So he is the subject, apple is the object, and ate is like the predicate. So you can put that as like a tensor. You can model like data sets with categorical features as like a tensor. Like let's say you want to predict like click-through rate for like different demographic groups for like a advertisement thing at Google. So like you have like gender, city, age group. Based on that, you're trying like, let's say, to do like tensor completion or something like that. So with that, let's get into Tucker decomposition, which is like one of the two most prominent decompositions. The other one is CP. I'm not going to talk about it. But what is Tucker? Tucker essentially tries to write the whole tensor as a smaller core tensor and a bunch of factor matrices. So the number of factor matrices is equal to the order of the tensor or the number of dimensions of the tensor. So if this is a tensor of order 3, I'll have 3 factor matrices. I have a core tensor of order 3. But the point is that the core tensor hopefully is much smaller than the actual tensor. And then how do I reconstruct the tensor? There is like this formula which looks very complicated. So let me explain it in like simpler terms. Essentially, like take the core tensor G, slice it up in like one way to get like a bunch of matrices, then multiply A1 with those matrices. So those are like a 2 by 2 matrices. A1 times them is like a 3 by 2 matrices. Concatenate them, you get like a larger tensor. Again, slice it in another direction, do the same thing with A2, and slice it in the third direction, do the multiplications with A3 and concatenate that. And then you get like a reconstruction of the original tensor. And what is the goal? Yeah, also like we show it like with this notation, which is like mod 1 product, mod 2 product, mod n product. So this is essentially in which way I should slice my tensor and do the multiplication. So what is the goal? The goal is to minimize the reconstruction error, which is the sum of squared errors. This is the Frobenius norm. I take the square, so everything is nice. And yeah, essentially it is just the sum of the reconstruction for the sum of the squared error for reconstruction of each entry. So what is the alternating least square algorithm? As you probably will already know, or like you can realize from this, is that if I try to find like the core tensor and all of these factor matrices at the same time, this is not a convex problem. This is like very non-convex problem. So how would I even go about like minimizing this? I do alternating least square, which is fix everything except one of the items and update that item. So the item could be the core tensor or could be one of the factor matrices. So one of the iterations is to fix the core tensor, all the factor matrices, and update the core tensor, which would correspond to a linear regression problem like this. And these are Kronecker products, which are defined as this. The only way I know how to define like Kronecker product is with like picture like this. Otherwise, it's just too complicated to show the indices. So the Kronecker product is essentially, if I have like a 2 by 2 matrix by a 2 by 3 matrix, this gives me like a 4 by 6 matrix. And each block of this matrix corresponds to one entry in this matrix, in the first matrix. So this red block corresponds to this one that is denoted by red. And then that's 1 times the whole second matrix. And then 2 times the second matrix would be the second block, the third block, and the last block. So this matrix has a lot of structure. That's probably what I'm trying to say. And because of that, we hope that we can solve it like much faster than like a general linear regression problem. And then like updating the factor matrices is I fix, like, let's say I want to update factor matrix I fix everything except AI, and then I minimize, like I solve this linear regression problem again and solve the problem. What is the difference between updating a factor matrix and core tensor? The difference is essentially this matrix over here, which is like a matricization of the core tensor. Why is this bad? Because it is destroying the structure, like the Kronecker product structure that I have here. I'm going to talk about how to deal with that later, but like for now, just believe me that just having Kronecker product is much easier than Kronecker product times some matrix. That looks weird.
Sorry, Mehrdad. How it destroys the structure of the Kronecker product, that matricization of G?
So I'm going to get into this later, but like essentially multiplying a vector with a Kronecker product can be done much faster than just multiplying a vector with a general matrix. The issue with this is that like y is a variable, all of these are fixed. So now if I like want to multiply like y with this, I cannot use the fact that this is a Kronecker product anymore. Okay.
I see. Okay.
Yeah, I'll get into it like later. I have a slide how to deal with that.
Okay.
So okay, let's first figure out how we are going to do the easy problem, the Kronecker product. So what are like the variables in my running time that I care about? So first of all, suppose the number of columns of AI is Ri, and we assume that they are larger than, like, the number of columns is less than the number of rows, and that is that's perfectly fine, at least for like the tensor decomposition case. In other Kronecker product regressions, it might not be the case, but here it is the case. And then I define R to be like R1 times R2 times 2Rn. And so what is this? This is essentially the number of columns of this Kronecker product. Okay. I'm not going too fast, right? Or too slow.
No, no, that's good.
That's good. Yeah.
And then what do I want? I want to solve this regression problem to 1 plus epsilon approximation. Why don't I want to solve it exactly? First of all, we cannot solve any regression problem exactly because of bit complexity issues, but I won't get into those stuff. Essentially, like, solving it approximately would be much faster. So there are previous work on this using like randomized linear algebra. What they do, let me explain what they do later, but here I'm just going to say like what their running times are. So you can use like some sampling approaches to get essentially like 2 different running times. One is to sample R over epsilon rows from this Kronecker product matrix, and then solve a linear regression problem with that. And then the running time you would get, don't think about like this first term, like this summation, because these are all lower order terms. But the last term has this like R to the omega, where R is this like exponential sort of term, right? Like, even if your R's are like all equal to 2, this is still like 2 to the n, right? So this is exponential. The other way you can do this is to sample from each matrix separately. Sample Ri over epsilon rows, and then take the Kronecker product of the sampled matrices and solve the regression problem for that. And that would give you like a running time like this, which is linear in R, but in terms of like your error term, it is exponential. Okay. And as I mentioned, like these red terms are the important ones, because the other terms are like lower order terms. So improving like these would be very nice, because these are like exponential terms. Like, it's either like R to the omega, which is exponential, or R times epsilon to the negative n, which is also exponential. So what do I do? What do we do? Essentially, our result is this. You can solve this in this running time. So the first part, again, like lower order terms, it doesn't matter. What is this complicated second term? So we have this R over epsilon, which is much better than like R over epsilon to the n. And these are like breaking R to 2 separate parts. Like I divide them to I divide the dimensions to a set S and its complement, and I take like the product of the size of the columns in set S and in the complement. And what is this MM? This is just matrix multiplication time. So multiplying like 2 matrices, like like an A by B matrix and a B by C matrix can be done in MM of A, B, and C. So if, for example, like this is like the multiplication of the running time of multiplying an A by A matrix with an A by A matrix. Okay, so this like R to the omega is essentially like MM of R, R, and R. Is things clear here, or? Okay, question.
I just have a quick question. Isn't this term still exponential in n somehow?
It is still exponential.
Right, you just split by 2 in the best.
It's just a little bit better.
Okay, okay.
So by a little bit, I mean this. So this is the improvement. Good question. We're not getting rid of exponential. I don't think that's even possible.
Yeah. Okay. Thanks.
Yeah. But this is the improvement. Like, if you don't want to look at like this complicated term, if you have like two different settings, you're either thinking like practically about the problem, which means that matrix multiplication takes time r cubed, or you're thinking theoretically about the problem in which the matrix multiplication takes r to the 2.372. And these are like the two settings I think about. So if it is a practical setting, I'm improving like the r cubed to r square. So this term would be like r square. And if it is theoretical, I'm improving like r to the 2.372 to r to the 1.626. I'm not making it polynomial time in terms of like the number of dimensions of the tensor, but improving like this exponential time. Like what I'm trying to argue is that because this term is exponential, even improving it a little bit is very helpful.
Yeah, that makes sense.
Yeah. So what are the ideas for this improvement? I'm just gonna dump like what are the techniques we use in this slide, but later I'm gonna explain like in more details like in next slides. And the stuff I'm mentioning here is used for everything. Like we do like ridge regression for Kronecker products as well, and we do a bunch of other stuff. So I'm gonna dump everything here, but I'm not gonna explain everything. But I'm gonna explain the simple case at least, like how we get there. So one technique is like using preconditioning. So this is essentially like when I don't have the actual inverse of a matrix, how can I like solve the regression problem? So this technique is called preconditioning. The other thing is that, as I mentioned, there are techniques to show that you can multiply a vector by a Kronecker product fast. I'm going to extend this to like sparsified Kronecker products. To go from the simple case to like ridge regression or factor matrix updates, we need a bunch of other stuff. Like we need to look at like block leverage score sampling. We need to look at like the SVD of the inverse of Kronecker products. And we need to look at like low rank perturbation of inverses. I'm not going to explain these stuff, but you need these to get to like more general cases. So, okay, let's get to like a sketching, and you mentioned like randomized linear algebra as well. So this might be interesting. So here's the goal now. I just want to show how you can improve the running time for the simple case. You just have a Kronecker product, you're trying to solve the linear regression problem. So how would I do that? Leverage scores are defined as this. So AI is row I of matrix A, and this is the leverage score of row I of matrix A. It looks complicated, but essentially what it means is that how important row I is in the row space of matrix A. So if, for example, I have like some row that is orthogonal to all the other rows, its leverage score would be 1. It means that it is very important. If I remove that row, it would change the row space completely. If I have like rows that are equal to each other, then their leverage scores would be small. Like if I have like two rows where they're exactly equal to each other, their leverage score would be like a half or something. Because even if I remove like one of them, I still have like the row space. And this leverage score sampling has been used to improve like the running time of solving linear regression problems. How would you do that? Suppose the leverage scores are given. I'm not going to talk about like how you would compute leverage scores in this talk, but like suppose they're given. I can sample this many rows of A based on leverage scores, based on a distribution I define on, based on leverage scores, then solve this problem, which has fewer number of rows now. Like the original number of rows was n, and 1, but now it is like d1 over epsilon. So this could be like much a smaller number of rows. And then this would give me a 1 plus epsilon approximation to the linear regression problem. So what do I mean by that? If x hat is the solution to this, then ax hat minus b is less than or equal to 1 plus epsilon times this. Okay. Any questions here? Okay. So what is the good thing about Kronecker products? The leverage scores are very nice. Like they deal with Kronecker product in a very nice way. So what is how do they behave under like Kronecker product? The Kronecker product of like the leverage scores of A Kronecker product B are just the leverage scores of A Kronecker product leverage scores of B. So if you want to compute the leverage scores of A Kronecker product B, figure out what is the leverage score of the corresponding row in A and the leverage score of the corresponding row in B and multiply them together. That would give you the leverage score for the row in A Kronecker product B. So this means that I can sample much faster from them as well. So I sample one row from A, I sample one row from B, and take the Kronecker product of those rows. And that would be a valid sample from A Kronecker product B. And then this is essentially like the result that like the result of like Dia et al. That I mentioned, like the previous work. You do the sampling, then you solve the solution, you solve the linear regression problem with the sampled matrix, and that would give you this sort of running time. For example, for when you have like only like 2 matrices in your Kronecker product. So where does this running time come from? This part of the running time, like NNZ of A plus B, that just comes from like how long it takes to compute the leverage scores of A and B. So this last part of the running time essentially comes from the fact that I need to invert this matrix. So this is the matrix that would show up in solving this linear regression problem, this one. And if I want to invert that, that would take this much time because it is like a D1, but D1 times D2 over epsilon by D1 times D2 over epsilon matrix. So in addition that this being bad in terms of running time, this is a very unstable process. Like inverting this matrix is a bad idea. We'll see in the, like, I have like a bunch of like experiments that I'll show you and show that this is very unstable, like compared to what we do. And to see like why do you need this inversion, like this is like exactly like x hat. Like x hat is defined as this this vector. So inverting this matrix, multiplying it with this vector, and that's x hat. Any questions from this slide? Okay. So what is the iterative method we are going to use? The iterative method is like a very classic thing. I think it is from 70s or even older. So it is called preconditioned Richardson's iteration. What it does is that suppose I have a matrix that spectrally approximates A transpose A. And what do I mean by spectrally approximates it? This is like PST, positive semi-definite ordering, like this notation. And this is between the matrix A transpose A and kappa times A transpose A. Then if I do this iteration, then in K iteration, I'll be this close to the actual solution, to the original solution, X star. And this is M norm of the matrix. So this M norm, because M is close to A transpose A, this M norm is also close to the A transpose A norm. So if you want to think about like A transpose A norm, that's fine too. And then go ahead.
Yes. So I always confuse with this kappa. This kappa is like a condition number or not?
No, this is not the condition number.
Okay,
This is just like some number. I shouldn't have picked
okay.
kappa for this.
I see,
Yeah,
because once I was reading the paper, I
this
had
is
the
like,
same problem.
yeah. For example, like this is 2 or 1 plus epsilon. Like actually with leverage score sampling, you can get like a 1 plus epsilon for this.
Okay, thanks.
So yeah, now I'm trying to solve this. But now instead of inverting this, I'm gonna invert the original matrix. Like the original matrix spectrally approximates the sampled matrix. This just comes from the leverage score sampling guarantees. So this is my original matrix, like without the sampling part, without S transpose S in the middle. And this is spectrally approximating this. So instead of this, I can invert the original matrix, like the gram matrix of the original matrix, which because of the Kronecker product structure is just this. So you see 2 things. First of all, I'm inverting matrices with a smaller condition number. Like the condition number is the condition number of Kronecker product is also product of condition number. So first of all, I'm inverting matrices with a smaller condition number. Second of all, this is much faster because these are smaller matrices. Okay. And then what would be I should have put this first. Now what is my Richardson's iteration? My Richardson's iteration look like this. So this is the matrix M inverse, which is my preconditioner, and this is like the part that depends on the sampled matrix. So now there are 2 questions. I know that if I have a vector, I can multiply it with the Kronecker product fast. And how do I know this? This is like, again, like a classic result. If I want to, like, let's say C is a matrix and vec of C is a vectorized version of that matrix. So this is a vector, vec of C is a vector. I want to multiply that with A Kronecker product B. How long does it take to do it? Like if you do it naively, like first compute like what A and B are, like A Kronecker product B is, and then do the multiplication with vec of C. That takes like this much time. Like if A is N1 by D1 and B is N2 by D2, this would take this much time. Instead of this, you can do like a 2 rectangular matrix multiplications and then take a vectorized version of that, and that would be equal to this, and that running time would look like this. Make sense? So good news, I can multiply xk by A Kronecker product B fast, right? What is the bad news? Now what do I do? Like I have this sample thing in the middle, and I want to multiply the result of this with this Kronecker product. So classic results don't talk about that. So we say that you can do that with like this a sparse matrix, like a sparse diagonal matrix in the middle as well. So what do we say? We say that suppose like your S is a diagonal matrix. Its size is very large, but it has like few non-zero entries. What are the number of non-zeros? Is R over epsilon. Then we can compute these 2 matrices in this running time. This is essentially like the 3rd term you see in our, like the last term you see in our running time, which is the improvement over R to the omega. Any questions here? Like I'm not going to explain how you do this multiplication, but just like what the result is. Is that clear?
So how did you use that property? So you use that vectorize of BC A transpose, and then you use, if I understood correctly, a Kronecker B vec of C. right? So instead of backup
Yes.
BCA transpose, you use the right-hand side.
No, no.
And then,
Instead
no?
of the right-hand side, I'm doing the left-hand side.
I see,
Yes.
okay.
Yes.
Okay, and then where is that
if
in this?
you look at this right-hand side,
Mhm.
this looks like this, right?
Right, yeah.
So instead of this, I can do this.
Yes.
Like I just matricize xk, put it
Uh-huh.
over here, do the multiplication, and then vectorize the result.
Okay.
Yeah.
Thanks.
So yeah,
So
this
just
is like
actually just to follow up so yeah, because then what, so a cracker b times x is easy to compute, but then S you said is a diagonal sparse matrix.
yes.
So isn't it somehow easy to multiply that by the outcome of a cracker b x? So yeah, you unvectorize like this, or you vectorize this matrix product, then you just to select the non-zero
So
indices, right?
if you do this, like if you compute this and then use the sparsity of this to do this faster, the running time we can get is like about like R squared. Like you don't need to compute all the columns of this,
Yeah.
right?
Yeah.
But you still need to compute the columns corresponding to the non-zero entries in this. And
Yes.
that would take like R squared over epsilon. But this running time is faster than that. This is like subquadratic. It's even
Oh,
faster
okay.
than R squared. Essentially, we give a version of like this identity that works with like sparse thing in the middle as well.
Okay.
Yeah.
Okay, good.
But yeah, you're
Thanks.
right. You can just use the sparsity of this to improve the running time to R squared.
Okay.
But for subquadratic, you need like more ideas.
Okay. Thanks.
Okay. So I think, yeah, I think you get like how we get like at least a simple version. So the idea, just to quickly recap, don't invert the gram matrix of the sample matrix, invert the original matrix instead, and then use like this sample version of Kronecker product times a vector to multiply it faster, and then you get improvement for the simple version. What do we do for the factor matrices? Like we have another result for like ridge regression, like regularized linear regression. In some sense, that is similar to this. In some senses, it is different. But I'm just going to explain like this part. So as I mentioned before, just Kronecker product is easy, but when I have this in the middle, it makes it like weird. Like I cannot like use this multiplication results here to improve the running time. So how do I deal with that? Essentially, I just change the variables. So instead of y, I solve the problem on z, but I say that z is orthogonal to the kernel of row space of Gn. So what does that mean? Any vector here, like any vector that looks like Gn transpose y, would be in the row space of Gn, right? So if I take the kernel of that kernel of Gn, kernel of the row space of Gn, this vector should be orthogonal to that. So if I find the vector z that is orthogonal to the to that kernel, it is a valid solution. Then I would just like multiply z by the pseudo inverse of this, and I get like a solution that is good. Now the issue is that I have a constraint in my linear regression problem. How do I deal with the constraint? The way I deal with the constraint is that I put this into the design matrix as well. But like, look at it this way. I have a matrix and a vector. I add this to the bottom of the matrix, and I add like a bunch of zeros to the bottom of the vector. Now, it essentially means that on those rows, my solution should be 0. Now I give this part of the matrix a large scaling factor. So if it deviates from 0, it would get like a large error. So it won't deviate a lot. Okay? Does it make sense?
Yes, but how efficiently can you compute the basis of the null space?
The basis of the row space. That would be efficient because the size of that depends on
So it's like you need to do an SVD of G basically, right? So this is the way I would see naively how to do it. You do an SVD of this matrixation of G, and this would give you a basis of the null space, but this is costly, right?
No, I think what we do is that you compute like a projection sort of thing. And the way you compute the projection is that you need to compute Gn transpose Gn. Okay.
Oh, and you do an QR decomposition or something like that to get
the
but the number projection.
But the number of columns of Gn is a small. Like the number of columns of Gn is like Rn.
But you still need to compute Gn transpose or the other way around. But
but
like
that
this will
would
depend on the product of all the R's except the small one, right?
Exactly. The running time would be mm of Rn, R and Rn. And that is small.
But you still got Rn, R to the n, right? You still get this.
No, not R to the n, R sub n. Like the number of columns of the nth matrix.
But how do you compute if you compute this gram matrix?
Sorry, this should be I first of all. And then the ith matrix, I mean, the number of columns of the ith matrix.
Which is okay. Because the way you were saying, I do the gram matrix, right? So like this GI transpose GI, or the other way. So this thing is small. That's okay. But to build this GI transpose is still a product. Like one of the dimension you're contracting is R to the n minus R to the product of R to the n minus 1, basically.
The good thing is that the longer dimension, the dimension that is equal to R over Ri, is in the middle. So
okay, but the matrix product, you still need R over Ri time to do it. Like it appears in there, right? You get
R over Ri, yes.
Okay.
But it is sort of linear in R, right? Like it is just R times Ri.
It's linear in R, right? Yeah, but it's still something that is exponential in the Ri, right? So if all of your Ri is equal to 2.
Linear in R is still exponential in the dimension of the matrix.
But also exponential. The part that I'm a little bit confused about is that now to compute this, you're still exponential in. So you still have a term which is R over Ri. And the improvement that you had previously from the previous result was to go from this R basically to R to something that is still exponential, but half of this, like the exponent is half of what it was before.
But that alpha is greater than 1. So this is still a smaller,
Okay.
But if you look at it, okay. So if you look at it here I have this R over epsilon.
It's still there.
Times these things, right?
So it's
essentially what you get is you get an Ri over here and an Ri over here, which is smaller than this.
Okay. I see. Thank you.
Okay. With that, let's go to the experiments and see like what's up, at least in practice. Our experiments are very simple. We just consider like the Kronecker product of 2 matrices. Oh, is there a question? I see a raised hand.
No, it's me that I didn't floor it. Sorry.
Okay. So yeah, we have like 2 Kronecker products. Both matrices are n by d. So if you look at like these plots, the first plot is d equal to 8, the second plot d equal to 16, etc. And the x-axis denotes n, and the y-axis denotes time. Okay. So if you just do like the naive baseline is just do all the multiplications, like don't use anything smart at all. And that, as you can see, like it is very bad. Like this is this blue line. And like when d is equal to 64, like you can't even like do that for large n. Like this was like, we gave it some time. I don't exactly remember how much time we gave it, but it didn't like do anything after like, let's say hours. So we didn't even like complete it. The Cron-Matmol baseline is the one that only uses like this identity, but it doesn't use any sort of like sampling or leverage score sampling or any sort of sketching or anything. And as you can see, as you can expect, is that when n gets large, that gets large as well. But it is like much better than like the blue line, which is like the very naive baseline. And then the purple and green are the ones that do leverage score sampling. So this DJSSW19 is the previous work Dow et al. They do leverage score sampling, but they don't do like this part of like, you know, doing the Kronecker times vector with like the sample thing. So as you can see, like two things that you can see here is that both our algorithm and theirs does not, the running time does not increase by much when you increase n. And the main reason for that is that it doesn't matter how large n is, because I'm only going to sample d over epsilon rows and solve the problem on that. So it doesn't matter how large n is. The only thing that matters is the size of your core tensor. But the other thing you can see is that like our running time, for example, for d equal to 64, our running time is like much smaller. Like this is like in terms of like seconds. So this is like 1200 seconds. Ours is like near like 0, maybe, yeah, maybe like 60 seconds or something like that. The other thing, like I promised I'll show you, is about the stability. So this is like the error they're getting, and like this is the error that we are getting in solving like the Kronecker product. For n equal to like 1024 increasing n. And this is like, this approx is essentially like the relative error. And as you can see, like you expect relative error to be something like close to 1. Because if it's not just like output vector of 0, that would give you like a relative error of like 2 or something like that. But yeah, this is very unstable. That's the takeaway from this. Is there a question? Go ahead.
Yes, your previous slide, could you go there?
Mm-hmm.
So I didn't get by in the last plot. The baseline and the fast Kronecker are doing the same, but in the third one, so it is not the case. You know what I'm saying? So so
Yeah.
for my understanding is that for the fourth plot as well, the baseline Cron-Matmol should not work very as well as fast Kronecker. Yeah.
So this is essentially because we are talking about practice. So I'm not doing fast matrix multiplication. My improvement is from d cubed to d squared. And this baseline Cron-Matmol is essentially doing the d squared as well. Yeah. So it's not exactly that, but you can think of it like that. Like they're the same because I'm not really doing like the theoretical result. If I did the theoretical thing, then it would be much faster. Also, the other thing is that this green thing is so large that is scaling these things down. That's probably you don't see the difference. Like here, like this is 30 seconds. So you see the difference, but this is now like 1,000. So you don't see the difference, but it's probably like there is a difference. Like if you look at this in the scale of like 30 seconds, you probably see a difference.
Yeah, got it, thanks.
Okay, how much time do I have? Do I have like 10 minutes or am I already?
Yeah, around 10 minutes.
Okay. So this is like the second part of the talk where I'm going to explain like this core shape thing. Let me at least try to explain what the problem is in 10 minutes. So yeah, this is just a recap of like what Tucker decomposition is, but you probably already know that, so I'm gonna skip this stuff. But here's the question. We are trying to do Tucker decomposition. You're taking a core tensor, your factor matrices, you're trying to optimize it with this like alternating least squares or other methods. But the big question is that how would I even pick like these RIs? Like I1 to IN come from like the size of your original tensor. But for R1 to Rn, that determines the shape of your core tensor, you're deciding what that should be, right? But how would you decide that? Like, how would I pick like the shape of my core tensor? Before like stating the problem formally, let's see whether that even matters. It turns out it matters a lot. Like let's say I want to do a Tucker decomposition of like some tensor, and for some reason I want to put like that decomposition on my phone, like some machine that has like limited amount of memory, right? Let's say it is like a layer of a neural network, and then I want to put that layer on like some device or something. So I have like a budget on how large my Tucker decomposition could be, and by how large I mean the total sum of the size of the factor matrices and the core tensor. And then like based on that, I want to see like how much like my error could be, like what is my relative reconstruction error, right? So as you can see, all of these gray dots are the possible decompositions with their relative reconstruction error. So what we did is that for this budget, pick all the possible shapes that has a size less than this budget, run ALS to convergence, and see how much the error is, okay? As you can see, a lot of shapes with this budget are not good. Like what you want is like some shape on this Pareto optimal front, right? Like you want something over here or near here. Like I don't want like some shape that is here. Like I'm paying that budget, but I'm not very accurate, so I don't want that. Is the problem clear?
Yes, I just have a question. So the budget is the number of parameters, right?
Yes, the number of parameters. The size of the core tensor plus the total size of the factor matrices.
Okay.
So let's define the problem formally. So these R1 to Rn is the shape of the core tensor, let's say. And we define this loss function, which is the minimum error you can get with this shape. So if I pick the best core tensor with this size, the best factor matrices with these sizes, what is the minimum I get? So that would be my loss. And then my problem, which we call like Tucker packing problem, would be this. So I'm trying to minimize the loss subject to the number of parameters being less than a budget. So this part is the size of the core tensor, the number of parameters in the core tensor, which is the product of our eyes. And this is the total size of the factor matrices. So factor matrix n would have like In by Rn size. Okay. And I want this to be less than a budget. Is the question clear?
Yes, just I have one clarification question. So IN is fixed. Here,
In
the
is fixed. Yes, that's right. In just comes from your original tensor. Like if your original tensor is like 10 by 10 by 10, In would be like 10 for all of them.
Okay, I see that.
So this problem turns out is very hard. The first reason is that even computing the objective function is hard. Like I cannot even compute this loss function L of TNR. because low rank tensor decomposition is an NP-hard problem. So how do I deal with that? Instead of this, we define a proxy function that approximates this up to a factor of n, where n is the order of the tensor. What is that? People have talked about like this sort of like proxy or loss or thing before. Like if you look up like papers that talk about like higher order SVD, these things are defined there. So these are essentially just the singular values of matricizations of your tensor in mod n. So if I matricize my tensor in mod n and take like its singular values and take the square of them and take the tail of them and take the sum of those tails, that would be like this proxy function. And the good news is that this proxy function approximates this actual loss up to a factor of n. What is the second problem with solving this Tucker packing problem? The second problem is that this constraint is very nonlinear, very non-convex. So how do I solve an optimization problem with this constraint? So the easy idea is to like just split the budget. If I split the budget to like a B1 part and a B minus B1 part, then what I can do is that to take the log over here. So instead of like a product, I would have a sum, and on the right hand side, I would have like log of B minus B1. Okay. Another difficulty that I'm not mentioning here is that in general, this looks very weird in terms of like an optimization problem. Like in an optimization problem, your like it's usually not that you're looking picking like a size or something. Let's see like how we model this, and this is how it looks like. So instead of like picking RNs, I define these variables like xin, and I say that the sum of them for each dimension is equal to 1. So essentially what I'm saying is that I want to pick one of the tails with this xin thing. And this PIN is just essentially the sum of the tail for the matricization of mod n. And then this part is just the splitting of the budget constraint. Go ahead.
So I did not understand what's xin. It's the singular values.
No. The sigma ins are the singular values.
So what's xin exactly?
Xin are just my variables in this optimization problem. I want to solve an optimization problem. So okay, let's go back to this. What is this problem? I want to pick a bunch of tails of these singular values, right? Like if you look at this proxy function, right?
Yeah.
So show the tail that you want to pick with xi's, like this xin, like for mod n, if xin of n is equal to 1, it means that I'm taking the tail with in, like from in plus 1 to the rest of the singular values. Okay.
I see. Yeah, thanks.
And this is the splitting part. So I want the size of the core tensor to be less than like log of B1, and I want the total size of the factor matrices be B minus B1. This is very complicated. I'm not sure if I'm clarifying anything. So essentially, like if xin of n is equal to 1, it means that Rin is picked in this problem. Okay. Okay. So this is the problem I want to solve. If you look at this, like if you really look at this, these are like two knapsack constraints. And this is essentially like a knapsack constraint, like two knapsack constraints with like a partition matroid constraint. In general, that problem is NP-hard, like people have shown this. But one might think, okay, I have like more structure here. I know like something about my tails, like the tails of singular values, because singular values are positive, they're like going down. There are like more structure to this problem. So one might hope that this is not NP-hard. The bad news is that even this is NP-hard. The proof is actually like very nice. Like if you had time to look at it, it is a very nice proof. And then like when a problem is NP-hard, what do? We try to approximate it. The good news is that there is a p-task for this problem. So a polynomial time approximation scheme. What does that mean? It means that for any epsilon, I can solve this problem to 1 plus epsilon accuracy. Like for any constant epsilon, I can solve this to 1 plus epsilon accuracy in polynomial time. But of course, like the running time is exponential in epsilon. But I'm taking like a constant epsilon. And then this gives me like a 1 plus epsilon times n approximation to the core shape problem for the Tucker packing problem. This needs like an extra step. Why? Because this problem I'm talking about, I have already done the budget splitting. So it is not clear how many different options for this budget splitting I need to try. And we show that you only need to try like log many different like budget splitting. And that's like the last part of the proof, that we show that you can get like this approximation for the Tucker packing problem. Maybe let me just skip the experiments for the sake of time. But essentially, the thing is that this approach to use like HOSVD is much faster than trying to do like a naive greedy with like the actual loss. And then I want to mention like an open problem that would be related to like this reading group, which is to like I solved it like for one tensor decomposition, right? Like just Tucker decomposition. But Tucker decomposition itself is like a special case of, you know, like 3 tensor networks or tensor networks. For tensor networks, I don't know how to attack this problem. But for 3 tensor networks, there are ways to like model this. So 3 tensor network, it means that like when I'm merging my mods, I only like merge them once and going up. So you can model this problem again as a combinatorial problem. The difference would be in your constraint. So instead of 1 core tensor, I would have like multiple core tensors. Like in this example, for example, I have like 3 core tensors in the red nodes. And then this is like a, you know, much more complicated constraint to deal with. In only the Tucker, we just had like 1 term in this summation. It was just this, but now it is more complicated. So let me just quickly mention some open problems. So as I mentioned, like try to see like how we can like solve the best core tensor shape for 3 tensor networks. The other one is that whether we can do like for the first part of the talk, whether we can do like faster algorithms for Kronecker regression. I have thought about like to do this in linear time instead of like R to the 1.626. I still don't know how to do it, but I don't have any reason to believe that this is not possible in linear time, linear in R. And the last thing is that whether we can do this like faster algorithms, like whether like some structure in tensors could help to do like a faster alternating list square. For example, if your tensor is symmetric, can I do like this alternating list squares faster or not? Again, I don't know the answer. And that's all. And I think I'm over time.
Thank you so much, Mehrdad.
Thanks, Mehrdad.
Thank you.
I have a quick, very, very quick and minor question if you have time.
Yeah, sure, go ahead. Yeah.
Slide 18, the property that you define. Is it? I don't know if you know about the degree of freedom. I forgot so I saw it in one of the papers by Agniva. So sorry, the effective degree of freedom that they define they use it for ridge regression problem. I don't know if this proxy related to that. I don't know if you know about that.
No, I don't
That
know.
is
What is it called?
okay.
Effective,
It is a degrees of freedom.
effective degrees of freedom.
So the paper that I'm referring to is here, but maybe we can discuss offline.
Are you talking about like effective dimension or something like that?
No, this is the paper, and then the relation is the equation for.
Okay.
But I'm not sure if that. But here lambda is the ridge regression, but it is a regularizer of the ridge regression problem.
This
So if you
looks like
yeah.
Yeah, I think I've seen this paper before. I think they talk about. Okay, let me. Am I doing the control F? Yeah, I think this is effective dimension or something like that. I don't know why they call it effective degrees of freedom. But yeah, essentially, like when you do ridge leverage score sampling, what happens is that the like the sum of leverage scores in general is equal to the rank of the matrix. But when you do like ridge leverage score sampling, that goes down. Like it would be smaller than the rank. And then some people call that like the effective dimension, or in this case, it seems that they're calling it effective degrees of freedom.
I see. Okay.
I don't know exactly how it helps. Like I never got deep into these papers, but at least in terms of number of samples, it helps a little bit.
Okay. Okay, thanks, Mehrdad. Yeah, it was out of curiosity. Just.
Again, thank you so much. If there is no question, I stop the recording
Okay.
for the time.